Welcome to a video on capacitors and dielectrics. This starts in section 19.5 and falls through to the end of the chapter. There's information and very good examples throughout all of the following sections within the book, so please make sure to read through that material. Without further ado, here we go. A capacitor is an electric component that's used to store energy. It involves two electrodes or electrical conductors, often referred to as parallel plates, and they are separated by a dielectric. A dielectric is an insulating material, and this means that it holds the charge within. It doesn't allow the charge to flow freely. And capacitance is the ratio or the proportionality between the amount of charge on each plate and the potential difference between the two plates. This relationship here for capacitance is C is equal to Q. It's directly proportional to the amount of charge, and it's inversely proportional to the amount of voltage. So C is equal to Q over V, where voltage is the potential difference between the two plates. Now, we've already talked about with a parallel plate, the potential is how much a charge, how much work, it's the energy per charge given in the position between two parallel plates. Here now we're going to start talking about how that energy relates in storing this. So capacitance is the relationship between charge and potential difference within a capacitor. Once again, capacitance, it reflects, it's the relationship between charge and the potential difference, and it's that ability to store charge. So with a parallel plates, or two parallel plates, actually I guess it would only be like, you could say one parallel plate, because it means you have to have two plates that are, anyways, you have two plates that are parallel to each other. There's a potential difference between the two of them. Due to that potential difference, there is an electric field. The electric field between the two within a parallel plate capacitor, assuming that the area of the plates is much greater than the distance between the two plates, is going to be constant throughout. And it's going to be perpendicular to the two plates. So we've already talked about this with electric field before. Now, when you put in a dielectric, and a dielectric, again, is an insulating material, something where the charges are not free to move, within a molecule it becomes polarized. And this polarization produces its own electric field. And that increases the amount of, that's actually like where the energy is going into being stored within this dielectric here. So it's more that the plates themselves create this potential difference, and they create this energy there. And then this dielectric is able to store this energy. So, for example, you can charge up a parallel plate capacitor. That energy is stored within that dielectric. And then you can unplug it, and that it will continue to hold on to that energy. And that energy can be held to be released at a later point.
All right, so here I have my little capacitor demo, and what I'm going to do is I'm going to show the capacitance, I'm going to show the plate charge, I'm going to show the stored energy, and I'm also going to throw on the electric field detector, and I'm going to throw on the voltmeter here. So here I have the voltmeter. I'm going to put the time here and here to tell the volts. So we have a potential difference right here between these two plates of 0. We have a 0 electric field in between the two of them. So now what I'm going to do is I'm going to take my battery and I'm going to turn it up here, maximum voltage, boom. So I have 1.5 volts. And if we wanted to go through, we can calculate out the electric field based on the difference between the two. So it increases because it's due to 10 millimeter difference between the two of them. So now we have right here, we have an electric field. We can see the total electric field within the plate is 150 volts per meter, which is the same thing as saying joules per coulomb. Excuse me, it's the same thing as saying newtons per coulomb. I have to pause and think about that for a second, because a volt is a joule per coulomb. So now I move this back, we see this the same field. I can actually show the electric field lines, boom, they're all straight, parallel, moving through. It's constant, I move it up and down within there. The electric field is constant within this parallel plate capacitor. Next, turn off those just to make it easy. Now, what I'm going to do is I'm going to start sliding in this dielectric here. This dielectric, it has, look here, we have a dielectric constant of 5, so it's going to increase the capacitance by 5 times when we move it through, so 5 here, so it should go up to about 4.5 times 10 to the 12th, or times 10 to the 13th, which will, get in there, capacitance keeps moving up. Now, as we notice, as I start moving it in here, there's more charge getting built up here. This means that the battery is having to add more charge on top of each plate in order to maintain this potential difference. Now, this potential difference here is not changing. The potential difference here is not changing. So as I add in the dielectric, there's more and more charge getting built up. So there's more charge getting added on top of each plate. Notice here how within the dielectric itself, there's polarization of the individual molecules. So there's polarization right here. Now, if I actually go ahead and put the whole dielectric all the way in here, boom, we have there 5 times as much capacitance, so 5 times that ability to store energy. And we'll zoom out, so kind of, okay, we go up there a factor of 10. We have increased the amount of charge on the plate, boom. We've increased the amount of stored energy between there instead of just having it be a vacuum, or like air is pretty close to a vacuum, not exactly, but there we'll have that. So we have increased the stored energy. And now if I zoom out here, we notice that the electric field, the total electric field between the plates, the sum is actually going to be, it's still 1.5 voltage difference between the two. And then we have an electric field created within the dielectric. So the plate is adding more charge on top to maintain this 1.5 electric potential difference between these 2 points here. That's what this battery is doing. All right, so I go through here and I'm going to disconnect the battery here. So I disconnect the battery, and we notice here that the amount of charge stays the same up here. It didn't just disappear just because I disconnected the battery. Because now there's this stored energy right in here in this capacitor. And what happens is this capacitor takes a long time within a kind of electrical sense. It takes a long time for it to store up this energy. So when you have a battery or some small within a circuit, it takes a while for it to provide the energy, especially in a different types of electrical circuit. It may take a little bit of time for it to build up this amount of energy or build up this charge on the plates. And what happens with a capacitor is you can release this amount of charge or release this amount of energy very fast, very quickly. And so that's something that a battery can't do. Batteries are good at providing constant energy throughout a source, or a circuit is good at providing constant energy throughout a source. And what we have with a capacitor is it can provide a lot of energy in a very quick amount of time when you discharge this capacitor. So we'll talk about that more with discharging capacitors a little later on and exactly what you do to do it. But understand that now within this setup here, we have this stored energy. We have amount of stored charge up here on the top, and we have this dielectric. So here we have it, and now what I'm going to do with this is I'm going to show you what would happen if the battery would act as some sort of device like that's going to take that energy. So we've set it down to 0 right here. Boom, 0. Now, when I move the dielectric in there, that's not actually happening. The dielectric is stationary, and what it is the battery takes a while to build up this charge. But so when I go and complete, let's say I complete another terminal or something like that, complete the circuit to, say, a flash bulb or a defibrillator, for example, all that energy is going to get used up, and all that charge is going to go away very quickly. So it just happens right away. So if I click here, boom, charge goes away, energy is all used up, and it happens over a very quick amount of time. So that I can increase the amount of energy provided by a battery by adding a dielectric and creating this capacitor, and I can use that energy all at once.
Now we want to look at, and I want to go back and kind of go through the steps of how that we can talk about a parallel plate capacitor and how we can calculate the capacitance of it, or its ability to store energy. So first off, we have that the electric field depends on the potential difference between the two plates and the distance they are separated by. This is an equation that within your textbook there, we talked about a little bit, the idea of electric potential is the difference. This is also known as the voltage. So we have electric fields depends on the voltage and the distance between the two plates. Then, if we think back to before to chapter 18, we realize that we have electric field is equal to, within a parallel plate capacitor, it's also equal to the amount of charge on one plate and the area of that plate. And it also depends on the permittivity of that free space. So now if we set these two ideas equal to each other, we get that the charge divided by the permittivity of free space, epsilon naught, and the area is equal to the voltage, which we can rewrite using the capacitance equation as the charge over the capacitance divided by the distance. From here, we just rearrange this to solve for our capacitance, and we will get that capacitance is equal to, or capacitance depends on the permittivity of free space, the area of the parallel plates, and the distance between the two of them. Then, if we add in dielectric, we get this constant K, and K is the dielectric constant. So different materials have different values of this, and it depends on or increases the ability to store energy within a capacitor. Now, the amount of energy stored within a capacitor, we can calculate it one of two ways, which we've already seen after doing the activity in class. U is the amount of energy stored energy. Potential energy is potential energy of a capacitor, U sub C. So we have 1/2 capacitance times voltage squared, so that could be the voltage across the capacitor right there. Or we can look at it in terms of charge, whereas the amount of energy stored is 1/2 the charge on each plate divided by the capacitance. All right, quick little sample problem. First off, a defibrillator is a tool that is used to store up energy to give a shock to restart a heart back to its normal and regular beats, regular rhythmic beats. So a defibrillator unit contains a 150 microfarad capacitor that is charged to 2,000 volts. The capacitor plates are separated by a 0.1 millimeter thick dielectric with a constant of 300. That's a dielectric constant of 300. First off, what is the total area of the plates? So you can rearrange the equation and solve for that. Second, what is the electric field strength within the capacitor? So look back at the different equations and how you have to go back to calculate the electric field strength. And third, what is the total energy stored within this defibrillator unit? Thank you very much and have a good night.